Every business leader, well, everyone running anything really, grapples with this question. How do you actually set your prices? Not just cover your costs, but really maximize what you can make. It's such a core challenge. So today we're doing a deep dive into the fascinating world of theoretical pricing decisions. Our mission really is to unpack the basic economic ideas behind setting the best price. We'll be looking at insights from our sources, covering things like, demand curves, how revenue changes, marginal costs. We'll look at it using tables, which is kind of intuitive, but also using algebra for more precision. It's all about figuring out how these economic tools can help businesses make smarter strategic moves.
Exactly. And it's important to remember this isn't just crunching numbers. It's really about understanding the relationships underneath all that.
Yeah.
The things that actually drive how markets behave and, well, your bottom line. We are focusing today on these, let's call them theoretical approaches. And you'll see they need quite a bit of detailed economic information. It's a great framework for understanding the why, but maybe not always what you'd use day to day if you don't have all that data. We can maybe talk about more practical ways in future deep dives.
Okay, great. So let's start with demand curves. Can you sort of unpack those for us simply? They basically show how the price of something, let's call it P, affects how much people buy, Q, right?
That's it. It's that inverse relationship. Yeah. Usually price goes up, quantity banded goes down. Yeah. And for this discussion, we're keeping it simple, thinking about straight line demand curves. Quantity on the bottom axis, price on the side axis. So a line sloping downwards.
Right. And the sources give a neat example, a product where if you drop the price by $20, you consistently sell another 1,000 units. So think about the extremes. At $180, the price is so high, nobody buys. 0 units sold. Demand is choked off completely.
Mm-hmm.
But, and this is theoretical, of course, if the price was 0, you might sell or give away maybe 9,000 units.
Right, the maximum potential quantity.
Okay, now here's where it gets interesting for me. What about total revenue? Price times quantity. At both those extremes, $180 price or 0 price, your total revenue is actually 0. Which seems counterintuitive at first.
It does, yeah. But what's really fascinating is what happens between those 0 points. Revenue doesn't just climb steadily as you sell more. The curve for total revenue actually goes up, hits a peak, and then starts coming back down.
Okay.
In our example of that peak, the maximum revenue you can get happens somewhere between selling 4,000 and 5,000 units. And finding that peak isn't just, a math exercise. It's a huge strategic signal.
Mm-hmm.
It shows you where selling more units actually starts to reduce your total income.
Even before costs.
Even before costs. It tells you when your pricing stops being helpful and starts, working against you just on the revenue side.
Okay, so if revenue goes up and then down, what's changing? What makes customers react differently? This must be where elasticity comes in, right?
Exactly. Demand elasticity. It's all about how responsive quantity is to a price change.
So on that first part of the revenue curve where it's rising, demand is called elastic. Like if the price drops from $160 down to $120 and sales jump from 1,000 to 3,000 units, the jump in quantity is proportionally bigger than the drop in price.
Precisely. The increase in quantity outweighs the price decrease. So lower price leads to higher total revenue. That's elastic demand. Technically, we measure it with the price elasticity of demand. If that number is greater than 1, demand's elastic. And in the example, I think it was 3.5 in that range. So yeah, very responsive. A price drop really boosts revenue.
Okay, it makes sense. But then on the other side of the peak, where revenue is falling even as you drop the price further, that's inelastic. Like say, price falls from $80 to $40, but quantity only goes from 5,000 to 7,000. Right. Here, the price cut is proportionally bigger than the quantity increase you get. You sell more units, but the price per unit has fallen so much that your total revenue actually shrinks.
You got it. That's inelastic demand. The elasticity value there is less than 1. I think the example had it at 0.3. So cutting prices further actually hurts your total revenue because people just aren't buying enough more to make up for the lower price.
Okay.
And just quickly, right at the very top of that revenue curve, elasticity is exactly 1. Unit elastic. That's where revenue is momentarily constant before it starts to fall.
This is fascinating. So elasticity tells you about the shape of the revenue curve. What about the change from one step to the next? Marginal revenue.
Marginal revenue, or MERS. It's simply the change in your total revenue when you sell one more unit. Or in our table example, maybe the change per 1,000 units.
Okay, so looking at the table, if going from 3,000 to 4,000 units takes total revenue from $360,000 to $400,000.
Right, that's an increase of $40,000 over 1,000 units.
So the marginal revenue for that block is $40 per unit.
Effectively, yes. That's the average MR over that range. And what's really neat is how MR links straight back to elasticity. If your marginal revenue is high and positive, it means demand is still pretty elastic, greater than 1. You're getting good bang for your buck selling more.
Okay.
But if your marginal revenue turns negative, that's a direct signal that demand has become inelastic, less than 1. At that point, selling more units actually reduces your total revenue. The price cut needed is just too damaging. It's a critical flag.
Okay, so we have revenue and how it changes, but the goal is usually profit, right? So we need costs.
Absolutely, can't forget costs.
The source gives a cost function. Total costs are $50,000, that's fixed, doesn't change with volume.
Like rent, maybe.
Right. Plus 65 times the quantity sold. That's the variable cost per unit.
Materials, maybe some labor, costs that go up as you produce more.
So how do we find the maximum profit? The source talks about an accountant's approach, which sounds like just building a big table, right? Calculate revenue at each quantity, calculate total costs, subtract costs from revenue, find the biggest profit number.
That's straightforward. You just lay it all out.
And doing that with this data, it shows the highest profit is $115,000. And that happens when you sell 3,000 units. The price for that would be $120.
Yep, the table makes it pretty clear. Find the peak profit point by just looking through the numbers. Very practical. But then there's the economist's approach. It offers a kind of shortcut, a decision rule.
Okay.
The economists say profit is maximized right where marginal revenue equals marginal cost. MR equals MC.
MR equals MC. Why is that the rule?
Well, think about it. If the extra revenue you get from selling one more unit, the MR, is more than the extra cost of making that unit, the MC.
You should make it. Adds to your profit.
Exactly. Keep going. But the moment the extra cost, MC, becomes more than the extra revenue, MR?
Stop. Making that next one would actually reduce your overall profit.
Precisely. So the sweet spot, the maximum profit, is right where they're equal. Or the last point where MR is still greater than or equal to MC. In our example, the marginal cost is just the variable cost per unit. So it's constant at $65.
Okay.
So looking at the table again, going from 2,000 to 3,000 units, the MR was $80 per unit in that block. Since $80 is greater than the MC of $65.
Definitely do that. It's profitable.
Right. But then going from 3,000 to 4,000 units, the MR dropped to $40. Now MR is less than the MC of $65.
So don't make that next block of units stop at 3,000.
Exactly. The rule confirms the same result as the table. 3,000 units, price of $120. But it's a more direct decision rule. Tells you when to push and, crucially, when to hold back.
That is elegant. But wait a second. The table works in these big jumps, like 1,000 units at a time. We found 3,000 units was optimal, but what if the real best point was, I don't know, 2,950 units or 3,050? The table wouldn't show us that level of detail, would it?
That's a really important point.
Okay.
You've hit on the limitation of the tabular approach. It's based on discrete chunks. For that finer level of precision, we need the algebraic approach. Using equations lets us look at things continuously, unit by unit.
Okay, so math time. How does that work?
Well, we start with the demand curve equation. The general form for our straight line was P equals ABQ.
Right. A is the price intercept, B is the slope.
Yeah. Using the data points from the source, we can figure out A and B. A is the price where quantity is 0, which was $180.
Okay.
And B is the change in price divided by the change in quantity. Price drops $20 for every 1,000 units increase. So $20 divided by 1,000 gives us
0.02.
Exactly. So our demand equation is P equals 180.02Q.
Got it. P equals 180.02Q. Now what?
Now, from that demand equation, you can derive the marginal revenue equation. There's a neat shortcut for linear demand curves. MR equals to 2BQ. Notice the slope is twice as steep.
Oh, okay. So just double the B part.
That's right. So for us, MR equals 182 times 0.02 times Q, which is MR equals 180.04Q.
Okay. MR equals 180.04Q. So now we have an exact formula for marginal revenue at any quantity Q.
Precisely. And now we can use the economist rule MR equals MC with much more accuracy.
Our marginal cost MC was constant at $65.
Yep.
So we set MR equal to MC. 65 equals 180.04Q.
You just solve that equation for Q.
Okay, let's see. Subtract 65 from 180. That's 115, so 115.04Q. Then divide 115 by 0.04.
And you
get Q won 2,875 units.
There it is.
Wait, 2,875, not 3,000.
Exactly. That's the power of the algebraic method. It gives you the precise point. The table, looking in 1,000 unit chunks, suggested 3,000 was best because the average MR across that whole 2,000 to 3,000 block was above MC. But this calculation shows that if you look unit by unit, the profit actually peaks at 2,875. Those last 125 units between 2,875 and 3,000, their individual marginal revenue would actually be slightly below the $65 marginal cost.
Wow, so the table gets you close, but the algebra nails it. You'd actually make slightly less profit at 3,000 units compared to 2,875.
That's the idea. It captures that fine-grained reality that chunks miss.
Okay, so the optimal quantity is 2,875 units. What's the optimal price then?
Easy enough. Just plug that quantity back into our demand curve equation. P equals 180 0.02Q.
So P 0.02, 2,875. Let me calculate that. 0.02 times 200,875 is 57.5. So P equals $122.50.
There you have it. The truly profit-maximizing strategy, according to this model, is to sell 2,875 units at a price of $122.50.
That's significantly more precise than the $120 price and 3,000 units from the table.
It is. It shows how these theoretical tools, especially the algebraic ones, can offer a much sharper picture for decision-making, assuming you have the data.
What a journey. We went from just understanding basic demand all the way to pinpointing the exact profit-maximizing price and quantity using both tables and equations. It really underscores how these maybe academic-sounding economic principles provide a really powerful framework for actual business strategy. It's not just theory for theory's sake.
Absolutely. If you connect this to the bigger picture, understanding these relationships between price, quantity, revenue, and cost, it lets businesses make informed choices. Much better than just guessing or following the herd. It really demonstrates the power of using data, even theoretical data like this, to drive decisions.
So as we finish up this deep dive, here's something maybe for you, the listener, to think about. We saw how powerful this is with detailed economic info. But what about businesses that don't have all that precise data? Think about like a small startup or a local shop, maybe running more on intuition.
Yeah, most businesses don't have perfect demand curves mapped out.
Right. So how could they maybe use some of the ideas we talked about today? Elasticity, marginal thinking, even without the exact numbers. What creative ways could they try to approximate this kind of thinking to guide their pricing? Something to mull over.